Hello. Wow, that was 12 minutes for parts A and B. Yeesh. Okay. Let's go to part C. Oh, let's start the timer on my phone so that I have some sort of, because I had no idea I had gone for 12 minutes. That was crazy. Let's see what's happening. A truck has a massive M and initially moves the speed of V naught. Consider two cases. The truck makes a gentle stop and the truck makes an emergency stop. Emergency stop! Boom, 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 boom. All right, so the truck has an initial momentum. Show in the diagrams what a gentle stop and emergency stop might look like. So the initial momentum should be the same for both diagrams, some sort of velocity times mass rectangle that shows a particular amount of momentum that the truck would have. I love how they use V naught in the stem and then VI on the um, diagram. That's not confusing at all. Okay, well, it's a free workbook, and I love to complain. So the gentle stop looks like, and so notice that the gentle stop is negative momentum, it's below the line. And for the emergency stop, it's below the line. So there's a negative amount of momentum in the impulse applied to the truck, or a negative amount of impulse to balance out the positive momentum the truck has. It needs to be the same. So that rectangle needs to be the same amount of area as the first rectangle, right? Your V here, right here. This rectangle and this rectangle have to have the same area. For a gentle stop, we're having a smaller amount of force over a longer time. For an emergency stop, it's a big amount of force over a short time. So there's a big negative force. Slamming on the brakes is a big negative force over a short time. But again, this rectangle is equal to this rectangle. This rectangle is equal to this rectangle. Zero momentum afterwards because we're stopping. We don't have momentum when we stop. And again, I think they left it up to you to decide how big the rectangles were. But again, a small force, right? Here's the negative force applied over a large time and a large force applied over like half the time or whatever. All right. We're using representations. We're amazing. The car company tests its safety features by crashing cars into barriers in its testing facility. The cars are all the same size and shape but are moving at different speeds and have different masses. Assume that the barriers are all identical and exert the same constant force. The barriers are identical. The rank the time it takes the cars to stop if the barriers apply the same constant force. So we have a 3,000 going at 10. We have a 100 going at 20. Wow. We have 1,000 going at 30. We have a 2,000 going at 20. All right, so I'm trying not to look at the answer. I'm thinking that it's going to take more time. So the bigger and faster you go, the more momentum you have, the same force is applied. So if the MV side, MV is equal to FT, right? The momentum, mass times velocity, is equal to the impulse that's provided when you crash into the thing. So force is the same. So the more MV you have, the more time you're going to have, right? It's just if the force doesn't change, the time has to be bigger. The biggest 2,000 times 20 is the biggest. I think 3,000 times 10 is 30,000. 2,000 times 20 is 40,000. 100 times 20 is tiny. That's like 2,000. 1,000, oh, that's 1,000. I can't even see this. Let's make this bigger. Well, it's bigger, but it's still fuzzy. 1,000 times 30 is 30,000. So we have a 30,000, a 2,000, a 30,000, a 40,000. So I'm going to say D is bigger than A. A and C are equal. And then B is the smallest one. Yeah, okay. And so justify your rankings. And I will just, like I talked about it, you can pause the video and read the red letters if you'd like. And we're already on D, so that was quick. All right, maybe it wasn't. A box is initially at rest, moves along a smooth horizontal surface, no friction. The horizontal force is applied to the box. The magnitude of the force changes as a function of time. So we're going up from 0 newtons up to 2 newtons. And then we're cruising along at 3 newtons. Up at 3 newtons. We're cruising at 3 newtons from 2, 3, 4 up to 5 seconds. Then we're slowly decreasing the force gently and evenly, amazingly, magically. from 5 to 8 seconds back down to 0 newtons. And then we're applying force in the other direction. So that'd be a negative force for 2 more seconds. All right. Take positive direction to the right. Sure. Rank the magnitudes of the impulse applied to the box by the force during each 2-second interval. So basically the area of the line under. So let's go ahead and get us a nice picture that the Burckhardt can draw on. Whoops. So what we want to do is like compare the so the area of this rectangle, triangle, the area of this rectangle. Oh, come on. Don't do me like that. Oh, that was horrible. The area of this bit right here, which is some sort of weird shape. All right, the area of this little teeny rectangle, the area of this little teeny rectangle here. So I'm thinking that this one and this one are equal and they're the smallest. This is going to be the biggest right here. And then this one, and then this one, and then this one. Let's see, how'd I do? Yeah, so B, this is B. B is greater than C, which is greater than A, which is greater than D, which is equal to E. Woohoo! Justify your reasoning. All right, well, I did that. Part C, that's too big. Represent the data given in the force is a momentum versus time graph for the same kilogram box. So identify the equation. Force times the change in time is equal to the change in momentum. Change in momentum is equal to the area under the force time. So times 0. So basically you can just do the times 0. What is the plot the momentum as a function of time. Make a table if you need to. The area under the force versus time graph. What? So what? I'm not really sure what they did here. Where did these numbers come from? Are these just the points like here? God. Shouldn't it be like an area? Like from 0 to 1? What do they do? Can I make this bigger? Nope. I guess I can do that though. So right here at 1, we have, so that's like 1.5. Okay, and then at 2 is like, 3, is that 6? Okay, so am I on the right track? Nope. Maybe counting the boxes. 1, 2.5. And I'm gonna have to get back to you. I'm not really sure where they got how they got these numbers off of this graph. They were getting these numbers off of this graph, right? How did they get those numbers? We should talk about that in class. Please ask me. Let's work it out together. I could use some help. I'm a little stuck. But once we figure out where to get the numbers, then obviously we know how to make graphs, right? So what they did is they just, somehow they got these numbers off of this graph, and then they made this, then they made a momentum graph, which, you know, I get how to make a graph. So we're saying that the momentum is increasing and then decreasing. Well, yeah, sure it was. It was increasing. As long as force times time was positive, it was increasing. It was increasing exponentially here, then linearly here, then decreasing, and then it was going to the negative side. So yeah, that's the same. This graph tells the same story. I just don't understand where the numbers on the momentum side of this data table came from. Like, because I think that they should be like, the area here would be 1 times 1.5. Oh, divided by 2 is 0.75. Right. My bad. So this would be 1, 2, and that would be 1. Okay. Yeah. It's the number of squares. So just count the number of squares for each second. So this would be the area, yeah. So this is, a triangle is 1/2, 1 times 1.5, which is 0.75. Okay, I get it. So that's 0.75. And then at 2, it's 1, 2, and then this would be 1, but it's a half of 1, so it's 1, 2, 3. Yeah, there it is, 3. So at 3, it will be 2, 4, 6. Okay, and then it should be at 4. Looks like it's going up by 3 every time. 3, 6, 9. I guess I'm still a little bit confused. Where are we at? Oh, it took so long my phone fell asleep. 10 minutes? Okay, let's just stop. Well, we can't stop. We're still on D. We got to finish this off. This is one of those deals where they want you to use the graph above to calculate the velocity after 10 seconds. So starting with our formula, momentum is equal to mass times change in velocity. So putting the numbers in, 14.5 minus 0 is equal to 10 times the final velocity minus 10 times 0. The initial velocity was 0. So the final velocity is 1.45, kind of a roundabout way of saying that. If we can figure out what the momentum was at the end, which was 14.5, I guess it's the total area. Maybe this is a running total of the area as you go along. If the running total was 14.5, then that momentum is equal to the mass times the final velocity, since it started at 0. All right, we got to stop.